Hello and welcome to episode 4 of the FRC video series from Team 8590. Today, things may look a little bit different, and that is because we are in Scratch, the programming website for kids. But we have a good reason to be here because today we are covering PID. PID is a control system for FRC that essentially helps our motors be more accurate. And I'm going to get into that. So, first, we need to think about what are we doing when we try to get to a certain point. And you can see right here we have these orange and blue arrows. The orange is where we want to be, and the blue is where we actually are. And you got to think about this when we're using motors. So if I were to say, all right, I want to get to where this orange arrow is, right? And I've got this motor. I'd say, okay, well, I need to turn up my speed in the counterclockwise direction. But you can see if I do that, I would just, of course, pass it again and again. And so we kind of reach this point of like, all right, how do we actually get there, right? And so here's what it looks like, right? We have these three components, P, I, and D, standing for proportional, integral, and derivative. The first I'm going to talk about is proportional. Proportional states that the further away we are from our target, the more power we should put in, right? It's just logical. The closer we are, the less power we should put in. And so you can see, if I add that, you can see that once the proportional is working, when we are far away, yes, we start to speed towards it, but we often overshoot. But that's all right. This is the first step of tuning PID control. Tuning is the process of finding these values. Because you see, distance, time, and speed are always accounted for, but sometimes the proportional is more important than the integral, or the derivative is more important than the proportional. And by setting these values, we can realize for our exact situation what the best values are and what the best algorithm is. And this is the first step. You want to increase PID until you oscillate around your target, right? And you can see that right now we're going back and forth. And the issue, of course, here is that we are going back and forth and we're not exactly where we need to be. And this is where the D component comes in. D stands for derivative. I don't know if you know calculus, but I'm about to teach you some. They call me Mr. Kim. All right, so the derivative in simple terms is the rate at which something is changing, right? So if you have the position of an object, right, its rate of change in relation to time is its speed, right? The change in distance is the speed. And so the derivative of the distance is the speed. And you can take the derivative of a derivative in that the change of speed is called acceleration. So the change of speed, or the derivative of speed, is acceleration. And you may be asking, okay, but how does the calculus help? Well, in this case, derivative accounts for our speed, right? Our distance is a position. The derivative of that distance is the speed. And the speed is very important because you can see we are just moving in relation to how far away we are, and that's causing issues, right? Because we are moving way past where we need to be because we're only taking into account how far we are. We're not taking into account the fact that we're already moving at a pretty fast speed by the time we hit the middle. So when we increase D, and this is what you should be doing with an actual PID tuning exercises, you slowly increase D until you stop oscillating past where you need to be. And once you reach a point where your oscillations are minimal, that's a good D. So you can see we are still doing a little too much oscillation when I go to a new place. But if I keep tuning, eventually I'm going to reach a point where it now seems like I don't overshoot too much. And if I would really need it to be exact, I can have a very high D. But the issue is, now we are going slowly, right? And this is kind of a battle you will see in every tuning exercise, where in FRC, a lot of it is about going fast, right? It's about how many points can you get. And the faster your robot can do stuff, the faster you can get points. And for that purpose, there's this kind of race where you also want your proportional to be pretty high, but you want it to be high enough that you can not oscillate too far. In some cases, a little oscillation is okay, but in some cases, your oscillation might be something that breaks the robot, right? If you go too far and you have like a rotating arm on your robot and you smack the robot with its own arm and the power is too high, you could destroy the robot. Hence why you often don't want to overshoot. Again, it really depends on your case. Now, it's important to understand that like you don't always need all three of these. Usually you will need proportional, and usually you will need derivative, but not always. And only sometimes do you need integral. And I've kind of spoiled it now that the I stands for integral. Again, we're going to go back to calculus. You see, when D is the derivative and it's how fast it's going, an integral is almost like a reverse derivative, right? So if speed is the derivative of position and acceleration is the derivative of speed, then the integral of acceleration measures speed and the integral of speed measures position. And where this comes into practice here is that, again, I'm simplifying calculus. Just take a calculus class if you really want to understand this. But it's not just the position, but it's also the relation to time. And we see that here, it's actually the buildup of the position over time. So you can see our P, right, we've talked about this. It's about how far away you are. The further away you are, the more power you put in. The integral adds a step to that, right? It says, okay, if we are far away, then we put in, so-and-so amount of power, right? But if we are far away and it's been, say, 5 seconds and we're still not close, then clearly this is not enough power. And so it adds power, and it's kind of adjusting as it goes, right? And often in FRC, we're okay with just the P and the D, and that gets us to where we need to be. But let's say, we have a specific scenario where, let's say, we have maybe, our proportional is at 1 or something close to 1, and we have that oscillation. And our D is also equal to 1. And we have, less oscillation, but still a little bit. We can now add, you're starting to see some of the issues that can occur with integral. So here, we're going to reset like that. You can see that it will adjust itself and fix itself over time. And that's very useful when you're doing long-term things where you need it to be really, really exact. But in our case, we are not doing things over a long period, and so you will rarely see integral used when we are doing these calculations. And if that made any sense, then I'm very happy. And I would also like to recommend that you watch the episodes of the Zero to Autonomous series that's available on YouTube that talk about PID. In fact, I recommend that entire series. It taught me a lot of FRC programming. I think it could teach you a lot of FRC programming. But its explanation of PID, I just thought to be really good, and I had wished I had seen it much, much earlier when I was first trying to figure this out. So now we will look at what this looks like when we are programming. All right, so now we are going to look at PID in the code. And in this case, we are going to be doing an arm. An arm is a very common thing to use in FRC. I think all 4 years of our team's existence, at least actively participating in competition, we have used an arm. And it's very important because you need to reach a lot of things. And when I say arm, I'm not talking about, human arm. I am talking about something that pivots to different levels, right? And for that, we have a couple things that we're going to use here, right? So let's look at these first things that we create. We have a motor, of course. We're not going to spin anything without a motor, and we're going to call that the pivot motor. We have the PID controller that we'll be using, and we have the encoder. Remember, I've talked about in the past, encoders track rotations, and it's important to know where our motor is so that we can calculate things like its position and its speed, and we can take that and put it into the proportional integral derivative. I'd also like to mention, you can see as the reminder I set here says that with this 3-bore encoder, you need to make sure you zero it in revlib. If you just plug into the encoder and you look around enough, I'm sure you will find out how to click the thing that says 0 offset. And what that does is it ensures that that is the point that is declared as 0 for the motor, right? Because we don't want it to start at, say, half a rotation, but when we turn on the robot, it takes it in as 0, and now it thinks that that half rotation is the 0 point, and now everything you have is half rotation off. So it's very important that you are zeroing that and making sure that you configure everything correctly. Moving on, we then have the extended and retracted position. In this case, we just have 2 things that we're using. In some cases, you may have many points that you're trying to reach, but in this case, we're just using 2. Also, you have triggers. We talked about triggers a little bit before, I believe in episode 2, and this is a case where we are just creating some triggers so that we can have actions on what to do when we are at certain positions, right? And because we only have 2 points here, we simply say if you are, less than the retracted position, or if you are more than the extended position, then you're good. But in some cases, you might have to say between 2 values because you have different points it could be at. But this is just for one specific case where you are either all the way extended or all the way retracted. We then have our constructor. And as we've done before, we have to use our configurations, right? We've seen this before in the last episode, and it's not too different, right? We first instantiate it, and we do the same process where we set the 3-bore encoder to be something that is attached to one of the other motors, and we then create our configuration. In this case, we have the inverted set to false. The idle mode is brake, and this is usually important when you want to have something that usually stays where it's supposed to be. In this case, when the robot's active, you don't actually need to worry about that. We have the current limit that, as we mentioned in the last video, is kind of how much you can push against the motor before it'll give. And we also have the ramp rate. The ramp rate is the speed at which it's allowed to go to maximum power, right? So I believe in this case, ramp rate is 0.1 if you do the math for that, which you can probably find under the WPI library or anywhere on the internet. It will explain to you that takes about 1 second for the motor to reach 100% power, and that's just a safety thing. All right. You can also see we have this PID controller, right? And we set our values to 0, 0, 0, and that's just how we are going to do it. You can also see because we are doing the usual PID controller. In this case, we're going in one direction. And if we were going in 2 directions, then you could actually have your inputs go anywhere from -1 to +1, because this is what's going into our motor.set. And if you remember from the first video, that's a range from -1 to 1. So we want the calculation of our pivot PID to be somewhere between those values. So now let's talk about actually having methods for that. So to reach the top part, right, we are going to take our motor and we are going to set it to a whole calculation, right? It's like our set methods from before where we say 50% power, 25% power with a 0.5 or a 0.25, except now we have a calculation. And the calculation is going to take in a couple things, right? So first they need the position, and then they need a goal, right? In this case, the set point that we are looking for is 0. We want the encoder to read 0, right? And these are arbitrary values. Your situation may be different. That's up to you. And we also have the reach goal down, which of course is calculating, again, with your position, but now with a different set point. And what's important to remember is you're using this position to figure out your offset, right? Your distance from the set point, which is the P, and then the time it's taking, which is already in the WPI-lib program. It's already keeping track of that. That goes into your integral. And then it's taking the derivative of that position change to get your speed, which then goes into the D. And so if I was programming this in the same way I had done with the PID demonstration from scratch, you could see I would be slowly increasing this until it oscillates around. And it's important to remember that that program from scratch was a perfect area with no friction, right? In reality, your arms are often going to be made of aluminum, and that can be pretty heavy for one motor to carry. So you might have a proportional value, and you might just see nothing happening. That doesn't mean the motor's not putting out power. That just means the motor is trying to put out power, but it's being overpowered by that weight. So I might just increase this and eventually get maybe a value of 2.0, right? And I say, okay, now I'm seeing it oscillate around where I want it to be. This is great. Now I just want it to smoothly get there. And so I might increase this until I get something. And maybe I'm seeing it's going too slow now and I want to decrease it and I want to mellow it out to find the perfect point. And I'm going to act like this is a normal situation in which we're often not going to use the integral values. And so now I have this whole system just solving on its own. It's going to say, okay, we took the encoder position and we found our offset is, X rotations off from where we want to be. We are then going to multiply that by the proportional value, which is 2. And we say, okay, that's going into the output. We now say, all right, we also have this derivative value. We are going at this speed of maybe this many rotations per second. And we say, okay, now we're going to add this value, and it's going to be multiplied by this derivative value. And we're going to add this all together, and we're going to get the output, and we're going to set the motor to that output. I also want to cover in this video commands. So that is pretty much the whole PID section, right? We now have the motors spinning as they should. Now we have these commands which will show us how to do things that are a lot more easy and convenient, right? So we are simply going to say return run this and then : reach goal down, which is going to help us run this method. Because we are using this as a command, we can use some of these nice methods that WPI-lib offers us, such as the until. So we are going to be running this pivot calculation until we are at that point, right? And in this case, we might keep it running, actually. You don't always need to do it like this. Sometimes it won't be a dot until. Maybe it's a more active thing where it's continuously running. But this is just to demonstrate the benefits of using things as commands instead of methods, is that you get these special classes. And then, of course, we have the other reach goal up command. And we have some triggers that might be nice, right? Again, we mentioned triggers earlier. In this case, we're using a trigger to see if we are at position. Using math.util is near. This is not math.util, which is what you use in computer science. This will have to be imported separately, but it is a nice class to have, as it is very important to be able to do calculations in robotics. So much of robotics is math, at least for programming. I don't know how much for the other people, but for us, we do a lot of math. And once we have this, we can now take these commands that we've done and we can make a command of our own. And I'm going to use this arm action command that I've created. So there's a little pseudocode in here, but you can see this is kind of how you would do something such as the 2024 robot for Crescendo, where it was important to pick something up off the ground, then move an arm up, shoot out the projectile, and then go back down. And so this is what arm action will do, where you have this first one which says arm.reach goal up command, right? And so this will simply move the arm up, and then you might say have a new wait command. Maybe you have some camera movement or camera odometry that's like moving your robot to. Honestly, this wait command doesn't really need to be there. It's just if you did have other stuff going on, you might want to have it there, but in this case, not really needed. And so it says, okay, arm.reach goal up command, and remember we have the dot until. So it's going to move up until it's at the top, then it will end that command and move to the next. In this case, you would have then a shoot command to shoot out the projectile, and as soon as the shoot command is over, you simply reach goal down. And so it'll reach goal down, and then it'll have the dot until, where it goes down until it's at the bottom, and now you're done. That's pretty much it. And so if you go to the robot container, right, in this case I have set it so the right bumper is the binding, and instead of having, say, a joystick control how high up the arm is going, and then a button that you press and that shoots it out, and then you turn the joystick down, and the driver is like trying to balance the joystick to make sure it's at the right height. In this case, all of that is taken care of by the PID, taking care of the exact point that the motor will be at, and then you have your commands in a sequence so that the whole process is taken care of. Again, the best FRC teams have automated robots. Think about Mechanical Advantage, a very good team, though we did beat them in 2025, not to flex. But they are often one of the best teams because so much of what they do is automated, and that's kind of their pride and joy. And they're right to do so. It's a good strategy, and it makes them a good team, and it can make us a good team too. And that is today's video. Thank you.